Log on, tune in, find out. Another good idea from Cambridge.
I took the title of the conference very seriously, especially the last word, physics. And I was thinking over the weekend whether I can really argue that the world around us has positive characteristic, but it's very, very large, so large that we don't see it, and that we all should study modular representation theory. But then I decided maybe I shouldn't, and I decided to talk about an ongoing research project with a colleague of mine, Bruce Westbury. And there is an article there in the new title. And the point of that is, when we are young, we learn that there are 4 infinite series of Lie algebras, and there are 5 exceptional ones. Then, when we get slightly older, we learn that there are finite dimensional finite dimensional Lie superalgebras, and they're also all classified. But then, around 1999, this perfect picture has been turned on its head by Pierre Bourgel, who actually discovered that there is only one simple Lie algebra. And so all the others are just representations of it. And that's why it's called representations of the Lie algebra. So there will be 4 parts in the talk. There will be historic introduction, Then in part 2, I'll talk about prop of metric Lie algebras, And then in part 3, I'll describe Bourgel's universal Lie algebra. Bourgel's universal Lie algebra. And in part 4, I'll talk about Rosansky-Witten invariance. Rosansky-Witten invariance. So I'll use slides for some of the parts. So for historic introduction, I'll definitely use slides. And let me start with 1996 paper of Delis in CR Academy of Sciences, where he introduced what's now called exceptional series of Lie algebras. So what he said is, take a finite dimensional simple Lie algebra. So he wanted to do exceptional series. Take the highest root alpha, and take lambda, which is -6, and you use Killing form on alpha. And we call it parameter lambda. And then he considered the following series of Lie algebras. You start from 0, A1, A2, G2, D4, F4, E6, E7, E8. There is a bit of a random choice of parameter for Lie algebra 0, so I'm not sure why it is 5, 6. But otherwise, the things are somehow glued nicely together. So this is the value of lambda, and one particular fact is that the dimension of the Lie algebra is given by the following formula of lambda. And there is further evidence which comes from decomposition of first 4 tensor powers of G into direct summands, that somehow this decomposition somehow also behaves nicely. And he wrote nice explicit formulas with respect to lambda. Maybe there is one fun bit about this. that there are two further values for which all of this witchcraft makes sense. And this is lambda equal to -4, and this is lambda equal to -1/4. And when lambda is equal to -4, we have to get a Lie algebra of dimension 1. But one-dimensional Lie algebra is not simple somehow. It's terrible Lie algebra in this regard. So I think that one is probably OSP4 too. It's a super Lie algebra. There is another funny value, lambda equal -1/4. And there you have to get a simple Lie algebra of dimension 190. Now, this one is called E7.5, and it has its own wiki page. So if you use this as a criterion of existence, E7.5 exists because you can. Yes, but maybe not. That's what it says on the wiki page, yes. That it's a centralizer of the lone root vector on E8, but it's not somehow. There is one paper on it, and that's what answer has been suggested for E7.5. Yes.
But what picks out the exceptional series? Why those particular algebras?
Well, you see, there are 4 classical series, and then there are 5 sticking around, and then apparently A1, A2, and D4. D4 is exceptional. But an A1 and A2 fit into the pattern.
But what about A3?
No. That's not exceptional in that respect. A1, well, anyway, no, that's not, well, it won't satisfy the same, I think, conditions. Well, it won't fit in the same pattern. But wait, let's go to the next slide. And the next slide is 1999, Vogel's paper. And it's a beautiful paper, but it's only available on his webpage, as well as a few other papers, because you somehow can see that somehow it deteriorates slightly. So he's trying to prove this, trying to prove that, conjecturing it. So it's not in any final stage, but it's still a very beautiful paper. And essentially, let me draw the following picture. So one thing he suggests that there is this Vogel's plane, and this is my addition. So you can find in the literature a couple of Vogel's planes, and they're all different. And essentially, well, you can so what this particular picture contains, so it contains 4 lines, so a line at infinity, and 1 elliptic curve, so I wrote carefully their coordinates. And this is somehow all super Lie algebras, finite dimensional with metric forms, should be there. And maybe I'll roughly explain what this picture contains. So roughly speaking, if you take G, you pick alpha and beta gamma, which are Casimir's eigenvalues in the component of the second symmetric square. And then you consider it as a triple inside weighted projective space, a quotient of projective plane by S3. And these are somehow coordinates x, y, and then these are the equations. But as I say, this picture is rough, because somehow the true Vogel's plane is some kind of, so in his paper, Vogel's proved that there is only one simple Lie algebra over some ring lambda, and the true Vogel's plane is the spectrum of this ring, and this is somehow only part of the spectrum. You are worried? No? Right. So maybe a couple of more words about this picture. So this infinite line is super Lie algebras D to 1T, and elliptic curves are also super Lie algebras. And their intersection is OSP of 2, which is also in this infinite series of super Lie algebras. All exceptional ones, not from the Lie series, but usual exceptional ones lie on this line. SL2 forms a separate line. Maybe you shouldn't take this picture too seriously, but it's a nice picture. Essentially, well, yeah, maybe let me stop with this picture. Right? Now, back to physics. So there is some more serious physics here. And Rozansky-Witten around 1997 wrote quantum field theory. You take M, which is close-oriented, three-manifold, and they wrote X, which is compact hyperkähler manifold. And they wrote some quantum theory like that. And so the bosons of this quantum field theory are maps from M to X, and fermions are sections of some line bundle, of some vector bundles. But essentially, to get the partition function, you have to integrate over the space of maps. And this is toxic, so it's path integral. So they wrote it as a graphs, as a sum of various graphs of these two expressions. And the right expression turned out to be old. So mathematicians looked at it carefully straight after. And the right, this I gamma M turned out to be some invariant which was known. But B gamma X turned out to be new invariant. And the beauty of this invariant is not that it somehow distinguishes something interesting, because there aren't that many compact hyperkähler manifolds. There are just a handful of examples. But the fact is that it's all connected with various beautiful mathematics. So essentially, well, B gamma X belongs to this Dolbeau cohomology group of X. And for example, if you take a graph which is just line, you are going to get just the class of holomorphic symplectic form on X. Or if you take this wheel with n spokes, you are going to get a multiple of a Chern class of tangent sheaf. And essentially around straight after Rozansky and Witten, Kapranov and Kantsevich formalized this definition mathematically in two different ways. And my talk is somehow in line with Kapranov's formalization of that definition. Okay. Going to part 2. Now I have to talk about this prop of metric Lie algebras. So we consider the following category. Well, we call it S. And it's a symmetric monoidal category. And objects of S will be just natural numbers. And tensor product on objects is just addition. And morphisms in S from one object to another is either empty, if n is not equal to m, or it's symmetric group, if n is equal to m. And then we have to define tensor product on morphisms. And well, let me define the twist. So the twist from n tensor m to m tensor n. So you take the first, well, it's graphically you can write this. This is the first m, this is the last m. And the first m go here, and the last n go here. So formally, tau of I is equal to I minus n if I greater or equal, if I is greater than n, or it's equal I plus m if I is less or equal than n. And I also need a tensor product of morphisms, and this is also clear. You just, well, you think of this, what is f tensor G? Well, this is f applied to the first n, and G applied to the second n. Okay. So this little category is the simplest prop. It's somehow initial object in the category of props. And a general prop, and I think this term has been introduced by MacLean around 1965, if I remember correctly. And I didn't know whether MacLean was a fan of rugby and played as a secret kind of practical joke, or whether he didn't know the meaning of this word. I've been briefed by my older son over the weekend that the prop is one of the two players in the scrum who support hooker on two sides. So please correct me if I got it wrong, but that's apparently the...
But actually, for him it was for product and permutation.
Yes, that's... But maybe he was still a fan of rugby, no? Product and permutation category.
Some people swap from Hamiltonian to hang.
Well, anyway. So what is this? So it's a pair, PF, where one P is symmetric monoidal category. Symmetric monoidal category. 2, F from S to P, some tensor functor. And there are two axioms, 3, that objects of P are also natural numbers, and 4, that on objects n goes to n. I think that's enough. Right? Now, we consider the following prop. And this is what's called sometimes universal metric algebra.
What is n on the right? N P is a symmetric monoidal category.
Where n objects, this is natural numbers. Natural numbers, yes? And this is for any n from n, which are also objects of S.
So in other words, it's a symmetric monoidal category which is generated by one. Because these symmetric
Yes.
constructions are automatic.
Okay, so let me explain the one which is. Okay. So you, again, objects of L for Lie algebra, and that's universal metric Lie algebras, are natural numbers. And HOMA, you take a Q-span of all Jacobi diagrams subject by two relations, quotient by two relations. And a Jacobi diagram, you can think of this as a compact, you can draw it in plane, because can't draw things in 3 space. Some people can on a computer, but here, so it's a compact curve, so abstract compact curve, but it has finitely many singular points, which are trivalent singularities. So locally, it will look like this. And it has n plus m boundary points, which are n's like that. And so it's a morphism from n to m. So they are either labeled by 1 up to n primes, or by 1 up to m. And the last bit of data is a cyclic orientation of edges near each internal vertex. So if you have a vertex like this, so you can either orient them, well, there are two orientations, clockwise or counterclockwise. And these are the relations. So the first relation says that if you have a Jacobi diagram, and then you cut out a little piece which looks like that, then change in orientation just changes the sign. So it's a local picture. So the curve is big, but this is some bit of the curve.
This is the tensor product thing? This is addition being tensor product?
No, addition is not tensor product. Addition of this addition will be tensor product.
But that's why I asked the question.
Yeah, this addition will become tensor product after you specialize to a real Lie algebra. An IHX relation is some sort of Jacobi relation. And there is I think all of this comes from knot series, like Bar-Natan. And I think IHX is a nice name because it looks like I, H, and X. That's why they called it IHX
So in
relation.
particular, the fact that it's drawn in the plane is not really important, right?
No.
Because you can have intersections which are not trivalent vertices, which
Yes.
are not singular
Yes.
points,
Yes. So some. Yeah.
which are kind of.
That's you
Effect
can
of
see
the
the
picture.
immersion. Yeah. So composition of morphisms is given by, and tensor product of morphisms is given by sticking curves together. So here you have to glue ends. So this is from morphism from n to m, and this is from m to k. So just here I glued all the ends together. And tensor product is, well, it's by sticking things together as well. And the functor is clear. You just, well, it's lots of lines connecting element t with element sigma of t. Yeah. So so if you try to draw these things in R3, you are going to get lots of braids. That's why braid people are looking at it. But if you look abstractly, you don't have to do it. So any questions at this point?
Why is it called metric algebra?
Yes.
Usually metric algebras invariant.
Yes. I'm going to explain it in a moment. I'm getting to it. Because why is it called a Lie algebra? And even metric one? Well, here is what let's consider, first of all, the ring of scalars here, which is K, which is endomorphisms of 0. So that's 0 is the trivial object in the tensor category. So it's endomorphism. And this is quite big. It will contain things like this, for example. Yeah? So this is a morphism from 0 to 0. Let me call this delta. And it will contain things like that. So this is also morphism from 0 to 0. Let's contain it, well, this one naturally called theta. Because it is theta, right? And here it's a universal property. Universal property. If G is, well, let's add finite dimensional metric Lie superalgebra, Lie superalgebra over a field f of characteristic 0.
The linear form should be even. For superalgebras, there are two types of invariants.
Yes, I think E.
Probably E.
Yes. Let me answer yes. I'll have to.
Symmetric algebras are functors from this category to the category of reference, right?
Yes.
And these metric superalgebras are functors from this category to the category of supervectors. Monoidal, symmetric monoidal functors.
You can say, yeah. And that's what I'm saying. Then there exists a homomorphism from K to F. And a functor and an F linear tensor functor from, well, let me write it here. From, well, you extend the scalars to make them over, that's a category, and this goes to category of representations in G. And I'll describe essentially how it works, careful. Element n goes to a tensor product of n times. And then for all the other, for the morphisms, what you have to do, you have to take a generic somehow immersion into into the plane, and then look at various things that will happen. So essentially, triple intersections will go to a tensor product, will go to a Lie product. Then there may be things like this when you immerse it. This will go to a twist. So it's the one that sends AB to -1 in some degree BA. And elements like this will become metric. So will become, so this is invariant bilinear symmetric form. And things like this will become, well, some kind of Casimir. So you take over the dual basis this sum.
So why do you need characteristics here?
Well, not, I don't need it here, but I may need it for, at least for Vogel's Lie algebra, it's not immediately clear. So, for instance, in characteristic 2 and 3, I think his ring is non-commutative, his coefficient ring. So it's kind of.
As far as I understand, this is basically Barnatan's way of getting invariance of knots.
Yeah. That's it. Yeah. This is well known, and Hinich and Weintraub wrote it. So it's something very well known in knot theory literature. That's right. Now let me explain what Vogel has done. So far this Lie algebra L is metric. And there are lots of metric Lie algebras which are not simple. So Vogels managed to play around with it to define another probe, which is simple. So he managed to add an adjective simple to this Lie algebra. How did he do it? So let me explain what simple means first. So Vogel, well, that's part 3 of my talk now. Vogel has defined a probe, let me call it lambda hat, which comes from lambda, but with endomorphism, this end of 0, let me call it k hat, which has the following universal property, such that the functor L hat, you have to take a tensor product with the field F to G rep, is defined as soon as G satisfies the properties I'm going to list. So it's essentially defined by a similar picture. Well, the conditions are, first of all, G is metric or quadratic. It means there exists a symmetric bilinear form. The second condition is endomorphism ring of G as a G module is just a field. And the third condition is that the square, and here is the square, you take home G from G. What can you do with it? So you can, if you use multiplication from G, you can have a map home as a G modules from G tangent G to G. Or you can have a co-multiplication map because it's metric, so it's equal to its dual. So this implies G is isomorphic to G dual. And we get a co-multiplication map. We get a co-bracket from G to G, G dual. So you can go to home G, G, G dual, G, G tensor G. And then it can go to home G here. So there is a little commutative square like that, but the condition is that that square is Cartesian. So this has to be a fiber product of these two maps. Now, well, you left vertical arrow. You go from G tensor G to G by multi. Well, if I have a map F here, yes, then F of X tensor Y will be just equal F of X Y bracket. Well, this is, for instance, if you take one-dimensional Lie algebra, then this will be satisfied, this will be satisfied, but this will not, because all the maps will be 0 here. But Holmes will be one-dimensional. So this is field, 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 2 0 maps. Well, it's not Cartesian, because then this has to be 2-dimensional for being Cartesian. So the 0 Lie algebra is not there. So it's an interesting question to pose, classify such Lie superalgebras. So well, as far as I know,
Finite dimensional ones.
yeah. So all simple ones are there. Well, at least for Lie algebras, all simple ones are there. For superalgebras, I'm not sure about this condition. And this happens because, well, we can calculate this square.
For usual Lie algebras, there exist non-simple ones that satisfy the template.
I don't know. Do you know?
What about E7.5? Is that?
No. This 7.5 is not there. It's a gimmick. And so that's a bit unsatisfactory, since all the representations of this Warshall's universal Lie algebra are essentially simple Lie algebras, as we already know. So by representation, we can understand a functor like that.
Semi-simple. Will they work? Semi-simple.
No, that will fail.
Ah, right.
Somehow,
Right.
semi-simple, the endomorphism ring will get bigger.
No, I mean the last condition. The last condition.
I have to think if there are multiplicities. If there are no multiplicities, then the last condition will be true. So, I mean, it's a bit unsatisfactory. So Bruce has thought of finding examples elsewhere. Okay, so if maybe there are some other simple Lie algebras. Maybe it will be settlement. But maybe there are some other symmetric monoidal categories which have nothing to do with the Lie algebras, and which have nothing to do with vector spaces. But they'll have Lie algebras, and they'll be representations of that thingy. L hat. Now let me define L hat, because I'm a bit behind on my program. Where should I go there to define L hat? The key to understanding L hat is the following Warshall's ring lambda. And lambda is actually a vector subspace inside home in L. This is home in L. You take home from 3 to 0. So these are graphs which will have 3 ends. But you don't take the whole home. You take only skew invariance under S3, S3x here. So you take skew invariance. So skew invariance. And you add 2 more conditions. So you ask lambda to be spanned inside this invariant. These are things that spanned by connected curves with at least one trivalent vertex. Trivalent vertex. Well, it's a vector space, but why is it an algebra? Algebra structure. Well, so these things will look like that. So, and there is something more complicated going on inside. How do you multiply by another fellow like that? You just write it inside. So what you do, you pick some trivalent vertex inside B, and you just write A inside. That was a trivalent vertex inside B, and you just write A into here. And the point is that it's a commutative algebra, and let me show it on the slide.
So you pick any, or you
Pick
some-
any.
You don't
Pick any. There is at least one, so you can pick any.
And it doesn't depend.
It doesn't depend, yes. And it doesn't depend whether you write B inside A or A inside B. That's what Vogels has proved. So let me show you some picture. It actually, when I first saw it, it actually puzzled me why it's not independent. So I decided to show a little picture. So I take this element T, which is, well, it has, because there are no marks here, it means all the vertices are oriented counterclockwise, and I want to compute T squared. So, and I can do it in 3 different ways. So I can write T inside, well, inside one of these 3 vertices. Why is it independent? So let me do the following. So this fellow, that's why I wrote it in this left vertex, but I've drawn it separately. And this one, I've written it in the here. And, well, this fellow is a bit strange, but what it reads, so locally it reads I, H, X. So if I draw it slightly differently, this relation, I get this one minus that one is equal to this fellow. And this fellow is symmetric. So it's similarly I get this minus the, well, get symmetrically this relation. And this follows that this picture is the same as that picture in the ring lambda. So I think it's quite beautiful. And what Vogel's prop is, so the point is, this ring lambda will act on some of the homes, but not on every element of the home. So it's in, as soon as it's connected, it doesn't matter where you write this A in. But if there are 2 connected components, then you'll get 2 different results. And another possibility is if there are no triple vertices, there is nowhere to write. So Vogel treats it by forcing the ring lambda up on this category L by taking the following home. So it's home in the previous L. You force lambda upon it. And then you take a quotient by 2 relations, here and there. So if there is if this graph has any triple vertex, then for every triple vertex there is this relation. And this relation is for any line. Questions at this point? It's actually quite a cool ring, lambda. And what has been written is some kind of, is a vain attempt to draw spectrum of that ring lambda in my Vogel's plane. But Vogel has the following conjecture about the ring lambda, which I maybe want to state. So conjecture. And this is by Vogel. And you take the following elements. Well, let's take X, which is alpha plus beta plus gamma. And let's take omega, which is X plus alpha, X plus beta, and X plus gamma. And they're all elements, they're all elements in Q, in symmetric polynomials in alpha, beta, gamma. Then the Vogel's conjecture is that lambda is isomorphic to Qx plus omega Q alpha beta gamma S3. And so what Vogel has actually done, so he constructs a map that way, explicit map in his paper, but he can't prove that it's that this map is isomorphism.
But he knows where alpha and beta and gamma should go somehow.
Yeah, you can draw it. It goes to, well, alpha and beta, gamma do not matter, but since like omega, so you write it in terms, well, he writes elements like this. So I don't want to, I don't have time to explain the conjecture, otherwise I won't get to my talk at all. Because it's all preliminary material, essentially. But yeah, he knows where things goes, and he can, on a computer, he can check it up to degree 16 or something. And then
Is it known to be surjective?
no. Up to degree 16, I think. It's both surjective and injective. Or maybe surjective up to degree 11, injective up to degree 16, or vice versa. So he has done some calculations. Now, part 4. And I have 15 minutes to get to Rosansky-Witten invariant. And the point is that, well, Rosansky-Witten invariants are, in the way Kapranov used them, they give a representation of the ring lambda, of this universal Lie algebra L. But sometimes it also gives representations of Wojciechow's ring, and that's my point. It's okay? So let me start with complex manifold X. Complex manifold. And let's consider the following exact sequence of OX bimodules. So these are 0, OX, goes to differential operators of X of degree at most 1. And this goes to tangent sheaf, and this goes to 0. And this is sequence of OX bimodules. Then for each locally free OX module F, vector bundle, right? So if F is locally free OX module, you can tensor this sequence together and get 0 F dx 1 OX. So these two are not really bimodules. So these are modules. Left and right action is the same. But here there is a difference, right? So this is a true bimodule. So maybe dx f tx tensor f 0. So what I want to take this extension and call it anti-Atiyah class. Well, so let's consider AF. And this is class of this extension. And it belongs to X1 from T tensor F to F. And T is a tangent sheaf. The dual of tangent sheaf is a sheaf of differentials, omega X. So these are H1 cohomology of X omega tensor product with and F. So somehow this is anti-Atiyah class because it's the inverse of Atiyah class. But what this class does, to split this sequence, you need a connection on F. To split this sequence here, you need a connection on F. So if there is no holomorphic connection, this class is non-zero. So it's some kind of abstraction to existence of holomorphic connection here. So what Kapranov has observed, he observed two things. Well, essentially, Kapranov observed well, first of all, he observed that if you take this, well, a tier or anti-tier class on tangent sheaf, this belongs to a direct summand. Oh, we call it omega t. And he wants to think of that as supercommutativity. So he wants to think of this as supercommutativity. And maybe I should say RV first. Rozansky-Witten. I think they've seen it essentially. And Kapranov also. But want to think of this as supercommutativity, and then you want to think of Bianchi identity. So Bianchi identity as some kind of Jacobi identity. And if X is holomorphic also, so if X is holomorphic, symplectic, if X has holomorphic symplectic form omega, want to think of omega as a metric on some Lie algebra. So omega becomes a metric on super Lie algebra. And what is that? You'd have to take tangent sheaf and you shift it in degree 1 inside tensor category, inside derived category. So let me explain it slightly slower on a slide. So the last slide. Kapranov's approach to Rozansky-Witten invariance. Let's consider the following symmetric. Let's get rid of all these derived categories. We consider the following symmetric monoidal category. Its objects are pairs, locally free coherent sheaf on X and a number Z, a number from integer numbers. Then the home from one sheaf to another is actually independent of the number, it's just the total X between these two sheaves. And the tensor product, well, it's just a tensor product of sheaves, and you add the numbers. Why do you need the numbers at all? You need the numbers to have a super Lie algebra structure instead of a Lie algebra structure. So you take, well, that's the tau, and it belongs to X0. And that's the point. Then Tx with a number -1 is a metric Lie algebra, and it defines the functor. So from L, which was a universal metric algebra, to, well, you have to extend scalars. It becomes, the scalars from ring K become cohomology ring of X, and n goes to tensor power of a symmetric of a tangent sheaf. So let me explain a little bit. Let me say why this explains Rosansky-Witten invariant. Then there becomes the following gadget. So you just take, your graph becomes, you don't take any graph, you take an element of home from n to m. And then you extend scalars and you apply this functor f. Here. And this becomes an element of home from a tensor power n to tensor power m. So it becomes x. Well, this is equal to x from Tn to Tm. And T is isomorphic, so it's holomorphic symplectic situation. So it's isomorphic to H star power n plus m tensor power of cotangent sheaf. And inside this there is n plus m symmetric power, which is n plus m forms. And essentially gamma has k internal vertices. Then this f1 tensor gamma is essentially some class inside here. And then Rosansky-Witten invariance is -1. Well, you just take a projection of this class here. Maybe a couple of remarks before I go any further. I have -1 sign because I've chosen anti-ATIA class instead of ATIA class. So it doesn't really matter. And this Delbocco homology, if X is not compact, then this Delbocco homology is infinite dimensional. It's not so cool. But if X is a compact, then this Delbocco homology is finite dimensional, but there are just very few examples of them. Because holomorphic symplectic and compact, and I think I want color as well at some point, maybe I forgot to mention, that becomes a hypercolor, and there are very few examples. Now, I have 2 minutes left. So I want to finish with this conjecture. Due to Westbury, and if X is compact hypercolor and irreducible. And irreducible means two things. So it means it's simply connected, and it means the Hodge number 0, 2 is 1. And then there are even few examples of those. Then T x minus 1 defines a functor. Well, let me write it this way. H x of x. And here I have to put k hat, L hat, to tx minus 1. And these are representations inside category C that I wrote here. And as I say, these fellows are very rare. There are only 2 known infinite somehow series of examples and few exceptions. And so it's not that we are going to get lots of representations. Hopefully we are going to get very few new representations. But this conjecture is, so far we can check it for K3 surfaces, and that's about it. And I think my time is up. I have to stop.
Any questions? Doesn't seem to be the case. Sorry.
You mentioned that these are Rosinski with lit invariants came from you would like to compute some toxic path integral
Yeah.
that's not well defined. Is this construction motivated by you said that this is like a category of drive category of coherent sheaves. Is this motivated by some algebraic way of actually computing the integral?
Yeah, no, that's, I'm not sure that it's motivated by way of doing integral. And I'm not sure which construction you mean, but so their construction comes from physics. So they just wrote this integral as a perturbative sum over all the trivalent Jacobi graphs. And these guys, Kapranov and Kansevich, quickly figured out what they've done mathematically and made a perfect sense of it, right? And this invariance, as I say, there aren't that many compact hypercolor manifolds to distinguish. But they are very interesting because they are connected with lots of other things. And one of the algebraic motivation of what's going on here, that somehow what do we do in representation theory? So we want to prove a theorem for all Lie algebras. And sometimes it's difficult. You have to go A, B, C, D, and then you're stuck at F4, and then you give up at E6, right? And somehow this is a brave new view on the simple Lie algebra. So you can just try to work with the diagram. So what sort of things can you see? And in particular, so far there are very little we can see, because Lie algebra seems to be difficult. And what we are trying to do here, we are trying to construct new characters of Borgel's ring lambda, because this is just polynomials over lambda. So to understand this category, we want to understand this ring better. And we can see some examples arising in geometry.
Any more questions?
So, for the pedestrian approach, for just algebra, just a set of Jacobi diagrams.
Yes?
That's all.
Sorry?
Is there something more in what your assumption algebra? Just you wrote these diagrams in here.
Yeah, it's a category. So of course you can't have a proper algebra which will specialize to AN, and it will specialize to E8 of dimension 248. It's specialized to G2, which has dimension 14. I mean, there will not be a single vector space which will specialize to everything. So it's in spirit of Deline's conjecture. So what he conjectured actually, that there is some category of rational functions in lambda, some category which will specialize to all of his exceptional theories. And Borgel has done slightly better. He said, well, why exceptional? We can just write down which specializes to every simple Lie algebra that there exists.
Let's send the speaker.